Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series intended for the BSc Honours Physics students. We are going through a series of lectures on optics, and especially the section on diffraction. We have been seeing how the diffraction pattern occurs when light is incident on a straight edge, small circular aperture, opaque circular disc, then the cornospiral, and again narrow wire. Now these are the cases when light is incident on an aperture, a small circular aperture. What happens in the diffraction pattern? And these are things we have seen, and the contents of this lecture will be as follows: diffraction at a single slit and diffraction at a narrow wire. And the diffraction at a narrow wire is an interesting case, and I will come to that later. Prior to that, we will go through the diffraction at a single slit. In continuation to what I have been talking to you all these days, let me start with the diffraction at a straight edge, so that you understand what I mean or what you have to understand by diffraction. You all know by now the word diffraction refers to the fact that light bends around obstacles. This bending of light beam around obstacles is not the one which was being considered by Sir Isaac Newton, because according to Newton, light rays should travel in the form of straight lines. If light rays would have traveled in the form of straight lines, then what should have happened is, let us take this case. You have got a source of light, you have got a straight edge. What do you mean by straight edge? In the path of the light beam, this is source here. In the path of the light beam, I have a screen here. This is the AD that is shown in the diagram is the screen. So in the screen, when you have a screen, it is automatically obstructing the light. So below the screen there should be complete darkness, because the light rays are traveling in the form of straight lines as supposed by Newton. Therefore, what you should get is there should be complete darkness here and uniform brightness here. The point I want to emphasize again is, when light is coming, it is incident on a straight edge in a cardboard or some obstacle of this type, then below this obstacle there should be complete darkness. You have a shadow, right? You have got a shadow region. We explained the rectilinear propagation of light. You know, the rectilinear propagation of light is the one that was thought by Sir Isaac Newton, but the same thing was explained by the wave theory of light. Similarly here, when you consider light as made up of waves, things are becoming different. Therefore, what you expect is, what you find is there is a finite intensity even in the shadow region. You know, this is a shadow region. You should have got uniform darkness and uniform brightness here. But on the contrary, what you observe is there is some sort of intensity which varies gradually, falls to zero. This is a geometric shadow region. The shadow region, instead of uniform darkness, you got some sort of bright light coming here. And similarly, the region where there should be uniform intensity of light, the intensity of light should be uniform in the region from P to M. On the contrary, the intensity waxes and vanishes, waxing and waning, right? So the intensity becomes large and then becomes less, again it becomes large, and so on. So this gives rise to what we call as diffraction bands. The point I want to emphasize is light bends. This is a so-called phenomenon of diffraction, and this bending of light beam we have seen in the last lecture in detail with regard to the diffraction that is happening at a straight edge. So now in this lecture we will go to diffraction due to a narrow slit. Let us see where is the narrow slit. You have S is a narrow slit as is shown here. You have got a slit here, right, narrow slit through which light is coming, and it is passing through AB, there is opening here. Essentially S is a point source, AB is the narrow slit, and the diffraction pattern that you get here is the one that we should be studying in detail. The slit may be narrow. The second case will be, it may be wider also. The two cases which are to be considered are, one is a narrow slit and the second one is a wider slit. Now what happens to intensity at the point P and what happens to intensity at P double prime? These are things that we have to see, because this I show as a shadow region. Shadow region is because when light is passing through the aperture or the narrow slit opening here, narrow slit or opening, then light will be going in this direction, AE, right? Similarly from B, it will go to BF. This is the region from E to F is the region which will be illuminated. This is what should normally happen. E to F is the region where there should be illumination, and again this is shadow region. Now the shadow region, according to the older theory, the shadow region there should be completely darkness. And you know, when you talk of diffraction, things differ. I told you this is the shadow region. In the shadow region there is intensity, there is some light, and again you got the intensity of light in the, even in this region, where the region which is directly exposed from the light source, there also the intensity is not uniform. Therefore one can expect this kind of similarities in the case of narrow slit also. When light is passing through a narrow slit, you have a narrow slit here, you have a cylindrical wavefront, and let us first try to find the intensity at the point P. As I told you in the last lectures, because you are talking about the intensity variation, I showed you in some of the cases there will be, especially in the case of a circular aperture, when you got a circular hole, we saw bright rings and dark regions, and so bright region followed by dark region, bright region, and so. So when the intensity is going to vary like bright, dark, then one has to have the kind of the things that we studied in the case of interference bands, namely the case of constructive interference, destructive interference. And here, in order to explain the variation intensity, what Fresnel brought into the picture is splitting your plane wave front. You have a cylindrical wave front or a spherical wave front. When you take a portion of the wave front, it will be plane wave front, and so here also a portion of the wave front will be a plane wave front. The plane wave front, as you know now, will be subdivided into number of what are called half period zones without introducing the concept or invoking the idea of half period zones. You will not be able to explain the intensity that is obtained at P or the intensity that will be having at P double prime. I am talking about the intensity at P double prime shows that light is made up of waves, they undergo diffraction. Straight lines, then that should be only the region E to F should be eliminated. In the shadow region there should be complete darkness, but now in the shadow region also there is some intensity. The intensity that is found in the shadow region or the intensity variation in the region from E to F all ought to be explained by constructing what we call as half period zones. So let us now start with S is a narrow slit illuminated by monochromatic light. The length of the slit is perpendicular to the plane of paper. AB is the rectangular aperture parallel to the slit. MN is the screen. P is a point on the screen. I told you the point P, I will come to that later. P is a point on the screen at which we want to find the intensity initially, and then we go to B double prime. Where is P? P is in the region where light is directly falling on the screen, whereas P double prime is a point away from that region, or you have the shadow region. And XY is the cylindrical wavefront. This is the important point. XY is the cylindrical wavefront that you have here, right? XY is the cylindrical wavefront that will be divided into what are called half period zones. So on the screen, EF is the illuminated portion. You know, EF is the illuminated portion, and above E and below F, that should be geometrical shadow. Obviously, you should expect darkness. If the slit AB is wide, then with reference to the point P, the cylindrical wavefront can be divided into a large number of half period strips, and the resultant amplitude at P will be m1 by 2, where m1 is the amplitude due to the first half period strip. Now these things by now you should be knowing. You may have number of half period strips, but the resultant displacement at the point P will be m1 by 2. The fact is, the two things which are to be kept in mind, or one is the displacement caused by the light coming through the first half period zone is m1, the second is m2, third is m3, and so on. All these things are known to you, and the magnitudes of m1, m2, m3 will be gradually decreasing because of what is called the obliquity factor. And the most important point is m1 will be opposed by m2. Why should m1 be opposed by m2? There will be a phase difference between m1 and m2 and m2 and m3. The reason being they are the so-called half period zones. So the light coming from the first half period zone will lag or lead compared to the light coming from the second half period zone. They are called half period zones. That means there will be a time lag of t by 2, or a path difference of how much is the path difference? Lambda by 2, or a phase difference of pi. If a crust is coming from the first half period zone, light coming from the first half period zone at the point P gives rise to a crust, the light coming from the second half period zone will give rise to a trough, and the magnitude of the trough, as I told you, m2 will be lesser than m1. Therefore, one writes the intensity at the point P. How do you write the intensity at the point P? The intensity at the point P will be effectively m1 then minus m2. Minus m2 means because the light coming from the second half period zone will be opposing that which is coming through the first half period zone. That is the reason why you call them as half period zones. So at this period we will have a short break and we will resume after a break. Welcome back at the break. I have been talking to you about the method of calculating the intensity of light at a point P on the screen because of the light passing through a narrow slit such as AB. You have got a cylindrical wavefront XY. This cylindrical wavefront has been, a portion of it will be a plane wavefront obviously. Now it is divided into a number of half period zones. As I have been telling you repeatedly, the half period zones are called half period zones. The reason being the light coming from successive zones will be opposing each other because the time difference T by 2 is there, which causes a phase difference of pi or a path difference of lambda by 2. So at the point P, as I told you just now, if the light coming from the first half period zone is M1, the light coming from the second half period zone will be M2. M2 will be less than M1. The magnitude of M2 will be less than M1. Therefore, you have to have M1, you have to sum up M1, M2, M3, M4 and so on. The important point is M1 and M2 will be opposing each other because they are half period zones. So I showed you in the lectures earlier that if M1 is like this, M2 will be downward because they are opposing each other. Therefore, you should have the resultant displacement caused at a point P should be written as M1 minus M2 plus M3 then M4. So alternately you should have plus and minus signs, and the magnitudes of M1, M2, M3 will they keep on decreasing. We wrote down M1 as M1 by 2, then again M1 by 2 minus M2 plus M3, but M2 will be, because they are gradually decreasing, M1, M2, M3 they are gradually decreasing. M1 by 2 plus M3 by 2 will approximately equal to M2. It is something like you have 7, 6, 5, 7 by 2 minus 6, then minus 5 by 2. So 5 by 2 plus 7 by 2 will be equal to 6. Therefore, when the numbers are gradually decreasing, displacement is gradually decreasing, then the bracketed expression we showed earlier, something like numerically 7 by 2, then 6, then the other one will be 5 by 2. So 5 by 2 plus 7 by 2 will be equal to 3. Okay. So therefore, the bracketed expressions will automatically become 0. Therefore, you are left with M1 by 2. That is what I showed you just now. So let me repeat: the displacement, the resultant amplitude at P will be M1 by 2, because the values of the bracketed terms, as we saw earlier, will become 0. So the resultant displacement will be M1 by 2. So the point P will be illuminated. Even points very near to P will be equally illuminated. If the wavefront is divided with reference to the point near to P, the number of period strips above and below the new pole in the exposed portion of the wavefront will be quite large, and hence this results in uniform illumination. Now let us consider a point P double prime or P prime or P double prime. P prime is a point within the region where light is falling. So depending upon the number of off period zones that you will be having, which will be causing light to fall on P prime, whether the intensity will depend upon the fact that whether you have got in the plane wavefront you have odd number of half period zones or even number of half period zones. Therefore, the intensity at P due to the exposed portion of the wavefront A between A and O prime will depend on the number of half period strips present. Let me go to the point P again. At the point P, the resultant displacement that is caused will be intensity at the point P due to the exposed portion of the wavefront between A and O prime. Okay, you have got O prime is here, A and O prime, right? And so the will depend on the number of half period strips present. So the number of half period strips present in the plane wave front will decide the displacement or the intensity caused at a point P. We will pass on to a point such as P double prime. Where is P double prime? P double prime is a point in the geometrical shadow region. I will move on to the picture once again. You find P double prime, that is the shadow region. According to Newtonian concept, Newtonian corpuscular theory of light, the intensity at P double prime should be intensity at P double prime. It will be 0 because shadow. The shadow region, now because light is undergoing diffraction, bending of light is there, in the region P double prime, at a point P double prime, the intensity is not 0. That point should be understood. Based on the Newtonian concept, if you assume light to travel in the form of rays of light, there is no question of any intensity being found in the shadow region. The shadow region should be absolutely dark. But now, because you are talking about diffraction, that is the bending of light beam, so light bends at the point A, similarly at the point B. Now, where is the point O double prime? O double prime is here, right? And when you are talking about O double prime, this O double prime becomes the pole. Now, the half period strips will be here. The first half period strip may be somewhere here above the point A. So, the whole half period strip is like this. It is obstructed by the obstacle. You have got obstacle here, right? The hole is here, which will allow light. The narrow slit is here. But if you look at O double prime, if O double prime is the pole, if you got the first half period zone or half period strip, then it is completely obstructed. The second half period strip also may be obstructed. Then third one will be like this. The bottom of the third half period strip will give rise to some intensity at P prime. This point should be understood. I hope, let me repeat again. For finding the intensity at P double prime, okay, then you connect P double prime to S, okay, P double prime to S, and O double prime is the pole. With respect to O double prime, you have to construct the half period strips. The first half period strip will be completely obstructed by this red region, okay. The second half period strip also may be obstructed. You look at the third half period strip, it may be like this. Only the bottom portion of the half of the third half period strip alone will be giving rise to intensity. Then again, for the fourth half period strip also, only the bottom may be giving rise to the displacement or intensity at the point B, P double prime. These things we will see in the time to come. So, this is what I am going to discuss now. So, O double prime is the pole of the wave front with reference to the point P double prime. I showed that from S to P double prime you connect, then join S to P double prime, then O double prime becomes the pole. If the wave front is divided into half period elements, then the upper half of the wave front between X and O prime is cut off, as I told you, because the object is extending. The upper half of the wave front between X and O prime is cut off by the obstacle, and only the portion between A and B is exposed to the point B double prime. Therefore, the diffraction pattern that you obtain due to a narrow slit, it will look like this. So, let me spend some time. So, if you have a narrow slit as we have assumed so far, the intensity that is experienced in the region will be looking like this. At the point P, the intensity will be like this. It is a narrow slit, okay. If it is a wide aperture, then you see the point is, the intensity at the point P is like this, then it comes down, again goes up and so on. This is a kind of intensity variation that we experience around the point P, okay, when you have a narrow slit. If the slit is having a wide aperture, instead of a narrow slit, you have got a wide slit. In such a case, the light intensity will not be varying as shown here. Instead, it will be almost uniform, okay. The light intensity will be almost uniform when you have got a wide aperture. So, these are the things which are to be borne in mind, okay. So, let me again show them two cases, namely a narrow slit. A narrow slit is the one in which the intensity will be very large, okay, but in a wider slit, so there is the intensity pattern, right? You got these things people should do. You got a white light here, you got a narrow slit, okay. Here you see white slit, the slit is wide, the width of the slit. Here the width of the slit is narrow. The diffraction intensity is shown here, right? Here is shown here, that the light pattern. If you have a laser beam and allow the laser beam to pass through a narrow slit, the intensity that you get on the screen will be like this. You got the bright intense pattern of this shape will be obtained, and then you have got a darker region and so on. So here it is polar region, then there will be intensity will be here, intensity there again, these regions are illuminated, and that is shown here. This is the intensity curve as a function of distance on the screen, okay. So you got intensity here, which is much lesser than what you got here. So there is a very bright region, right? And the region where there is brightness, it falls far off from this region, but here it is nearer. So this is the kind of pattern that you get when light is passing through a narrow slit and then a wide slit. So the diffraction pattern, as it showed, the narrow slit will be like this. I am repeating the same pattern, same thing what I told you. Wide aperture will be like this, okay. So this is what we have should know regarding diffraction when light is passing through a narrow slit and a broad slit or a wide slit. So let me now more or less end up this section. Thus between E and F. E and F is that is a region where there is light is passing directly. Alternate bright and dark bands will be observed, and a point P may be bright or dark. Now consider the point P double prime, as I showed you in the geometrical shadow region, where we took O double prime as the pole, and the intensity at P double prime will depend on the number of half period strips exposed by the slit AB, whether the odd number of half period zones or the even number of half period strips. Those things ought to be taken into consideration. So the intensity distribution on the screen due to narrow slit, say less than the wavelength of light, a broad central maximum will be observed in the illuminated portion, and the intensity variation cannot be distinguished. The intensity gradually falls off in the region of geometrical shadow. The point is, the intensity gradually falls off in the region of geometrical shadow. Let me now summarize as to what I have done in this lecture. The cylindrical wavefront incident on a narrow slit can be divided into a large number of half period strips. The intensity at any point will depend on the number of half period strips. In the case of wide aperture, the intensity falls off rapidly in the region of geometrical shadow, and maxima and minima cannot be distinguished. In the case of a narrow slit, a broad central maximum will be observed. We will now pass on to the few questions related to the lecture delivered today. What do you understand by diffraction at straight edge? Comment on the intensity distribution of the diffraction pattern and also compare it with that of the interference pattern. How does the intensity of light on the screen vary in the case of a narrow slit and a wide aperture? With this we come to the end of this lecture, and we will discuss the problem of diffraction at a narrow wire, corner spiral and so on in the lectures to come. Thank you.